The first thing we learned about are protons. Protons are positively charged. They're in the nucleus of the atom. If I add protons to the nucleus, the type of atom changes. So for example, if I have 3 protons in my nucleus, I have lithium. Today, tomorrow, next week, 3 protons will always be lithium. As I keep adding protons, I'll keep moving across the periodic table. Now you'll notice here with my beryllium atom that I'm creating, it's telling me that it is a positively charged ion. I can see here it has a net charge of +4. That's because I have 4 protons, which have a positive charge, and no electrons. So in order to balance that out, I'm going to add electrons. So now I have a +3 charge, a +2 charge. You'll notice this net charge is becoming closer to neutral. Electrons are negatively charged. They are around the outside of the nucleus. Electrons are not anywhere near the size of protons. This is just a model. Electrons are teeny, 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 tiny and are around the outside, but they do have the exact same charge. So I'm going to go ahead and add 4 electrons so that my beryllium atom is not going to be an ion anymore. It is now a neutral atom. Now you notice I'm not really messing with neutrons right now, and that's because I'm not really interested in nuclear chemistry. However, a beryllium atom also has neutrons in its nucleus. If I click this button, I can see that this beryllium atom is unstable. It's unstable because it's missing the correct number of neutrons. But like I said, I'm not worried about neutrons today, just protons and electrons. Now, you'll notice something else happened when I added the electrons. Let me start over. I'm going to start building a carbon atom. So in order to build a carbon atom, I need 6 protons in its nucleus. So it has a charge now of a +6. I'm going to throw the electrons in here. You're going to notice that they're going to go to these rings. If I try to add this electron to this ring, the simulation won't let me. It's actually going to throw it to the next ring. That's because the inner energy level, this inner circle, only will hold 2 electrons. So in order to get it neutral, I'm going to go ahead and add my additional electrons to make it 6. So now I have a neutral atom, which is what we're going to be working with when we talk about organic chemistry. A carbon atom has 6 protons in its nucleus and has 6 electrons around the outside. 2 of these electrons are in the first energy level, and 4 of the electrons are in the second energy level. You'll see that I can change my model here from orbits to a cloud. And that's because the electron cloud model is what is currently accepted. Orbits are just a model to show us orbitals. A cloud shows us exactly what it might actually look like. Now, the electron cloud can be defined as the region in space in which there is a 90% possibility that electrons may exist. And these electrons are bouncing all over the place and buzzing around. So now we've determined what an electron is and what an electron isn't. We've seen these pictures before. We know that electrons don't orbit, and they're not in these orbits. Instead, they exist in these clouds. So now that we understand that, we can talk a little bit more about these orbitals. Now, when I bring this up, this looks really confusing. We have 4 different types of orbitals: S, P, D, and F. All these orbitals really tell us is that there is a high probability that the electrons will exist in these locations. So for example, in hydrogen, there's a high probability that the electrons will exist there. And then every element thereafter contains all the electrons before it. Now this can get rather confusing very quickly. If we look at the electron orbitals, you'll see here's hydrogen's high probability. There's helium, lithium, beryllium. Remember, every time you add a new electron, it contains the same electrons that came before it. So when you get all the way up to element 104, you're going to have 104 electrons with 104 unique places. Now, a couple things to remember about these electron orbitals. First of all, they're just a probability in space where the electron may exist. This is just the spot where they might exist. Secondly, each orbital holds 2 electrons. So the s electrons hold 2, and then we move over to this section. Each of these p orbitals holds 2 electrons. The third thing that you need to remember about electron orbitals is that, quite frankly, we don't care about all of these electrons and all of their places. Most of the time in chemistry, and especially organic chemistry, we are only talking about valence electrons. So we're going to make this a lot simpler. We know that carbon exists here on the periodic table, and we have been taught that carbon has 1, 2, 3, 4 valence electrons. You can see here it also has the electrons that come before it. So here are these first 2 electrons, 1, 2, and then here's electron 3, 4, 5, and electron 6, which gives us 4 valence electrons. Now, honestly, we don't care about most of the periodic table in organic chemistry, so we're only going to focus on these s orbital electrons and p orbital electrons. We don't really care about the d and f. But what I want you to look at is if the shape of an s orbital is this spherical shape, and the shape of a p orbital is this kind of propeller shape, then why is it that carbon gets its valence electrons to turn into this shape? So carbon has 1, 2, 3, 4 valence electrons. We can see that 2 of the valence electrons are s orbitals, and 2 of the valence electrons exist in the p orbital. So how does this and this turn into something that looks like this and reminds us of something that looks like this? Now you may see a lot of confusing things out there, things with electron configurations going all the way from S, P, D, F with a lot of numbers and a lot of things about energy levels, but I'm going to break it down as simply as possible and actually break it down to what's important to us in organic chemistry. So this is an s orbital. It's the lowest energy and it's the closest to the nucleus. You can see it has a spherical shape. Now an s orbital again means that it can hold 2 electrons, and this is the probability in space that those 2 electrons will exist. A p orbital has this propeller shape. Remember that a p orbital has 2 electrons that can fit in it. It doesn't mean that one is here and one is here. It just means that 2 electrons can fit inside this orbital and they exist in that region of space. So if I look here, here are my 3 p orbitals. The energy of the p orbitals is higher than that of the s orbital. Also notice that these p orbitals are right angles to each other, and each p orbital has a node right at the nucleus. So how are we going to get that shape of the carbon? In order to understand that, we need to understand something called hybridization. Atomic orbitals can be hybridized to generate orbitals of equal energy. We're going to watch how the atomic orbitals are hybridized into hybrid orbitals. The first one we're going to look at is called an sp3 hybridized orbital. So in order to do that, I need one s orbital, and then I also need to add 1, 2, 3 p orbitals. So you can see here I've got my 3 p orbitals and my s orbital. This does not look at all how carbon is going to bond. So I'm going to show you how these 2 orbitals become hybridized. Now what you see here is an sp3 hybridized orbital. You should notice that familiar tetrahedral shape. Now sometimes the atoms don't want to hybridize all 3 of the orbitals. So this time we're going to work on something called sp2 hybridized. 1 s and 2 p orbitals. We're going to again hybridize this. This becomes sp2 hybridized. You should recognize this shape as a trigonal planar shape. Now, this doesn't exactly tell the whole story because we know that by looking at the periodic table, we have one s orbital and 3 p orbitals. So I need to make sure that I also include that other p orbital. So now we have all of the orbitals accounted for. Now let's see what happens when we have just sp hybridized. One s and one p. I'm going to go ahead and hybridize those. This is sp hybridized. You'll notice here it looks linear, but I'm not finished yet. I need to add the remaining 2 p orbitals. So I have all 3 of my p orbitals. One has been hybridized with the s orbital, and you can see there the remaining 2 p orbitals. I'd like to take a second to tell you how to easily tell if something is hybridized. The easiest way in organic chemistry is to count how many things are around this central atom. So in this case, there are 4 things around this carbon. It is all 4 bonded hydrogens. In this case, there are 4 things around this nitrogen atom, 3 bonded hydrogens and a lone pair. In this case, this is water. There are 4 things around this central atoms. That's 2 bonded hydrogens and 2 lone pairs. Everything on this page is considered sp3 hybridized and will give us that nice tetrahedral electron shape. Let's talk about how to find things that are sp2 hybridized. When things are sp2 hybridized, it means that there are 3 things around the central atom. In the case of this carbon, there are 2 bonded hydrogens and there's this double bond. That means that this carbon is sp2 hybridized. You do not count the double bond as 2 things. You'll also notice things that are sp2 hybridized have this trigonal planar shape around them. Both of these carbons are sp2 hybridized. This is a familiar thing that we see all the time in organic chemistry. It is a C double bonded to an O and then bonded to other things. This right here is called a carbonyl group. The carbonyl group is sp2 hybridized because the carbon is double bonded to this oxygen and single bonded to each hydrogen, which means there are 3 things bonded to this central atom, which is what makes it sp2 hybridized. Now let's take a look at sp hybridization. It doesn't come up very often. Look at each one of these carbons. Both carbons are only bonded to 2 other things. They only have 2 things around them, no lone pairs. So each carbon is sp hybridized. You'll notice here in this drawing, it's reminding you that this carbon here is sp2 hybridized and this carbon is sp3 hybridized. You're counting 1, 2, 3, 4 is sp3 hybridized, 1, 2 is sp hybridized, and 1, 2, 3 is sp2 hybridized. Let's see what happens when bonding occurs. Let's go back to our sp3 hybridized atoms. So I'm going to add one s orbital. Here are my 3 p orbitals. I'm going to go ahead and hybridize those. There's that nice trigonal planar shape that I'm used to seeing when I see carbon often bonding. I'm going to add a second atomic nuclei because this time I want to bond. So I'm going to again add an s orbital to it and 3 p orbitals. I'm going to hybridize those. So now I have 2 atoms, could be of carbon here, that are both sp3 hybridized. Let's see what happens when I make a bond. This bond right here is called a sigma bond. It's the first bond that's formed, and it's the bond that forms along the inner nuclear axis. So that's a single sigma bond. One interesting thing here that you'll see about this single bond is that it can freely rotate. And we've talked about this a lot in this class, but that single bond can rotate easily. We're going to see how a double bond cannot do that. So let's go ahead and make an sp2 hybridized atom. Let's add a second sp2 hybridized atom. And we could bond these right now if we want, but don't forget we are missing our last p orbital. So let's not forget to add our final p orbital. You need to have 3 p orbitals. So now you can see we have sp2 hybridized atoms, 2 of them, and they have this extra p orbital. Let's see what happens when they bond. Now we have formed a double bond. This is what a double bond looks like. Notice the hybrid and the p orbitals overlap to give 1 sigma bond and 1 pi bond. The pi bond goes above and below the internuclear axis. Now you'll notice when I try to rotate, it breaks that pi bond. The pi bond will not stay when I try to rotate it. That's why we'll say that things that are double bonded cannot rotate. Now you can even turn it, look down in this direction. When you rotate it, you'll notice that that bond has been broken. The last thing that I'd like to show you is what happens when you bond sp hybridized orbitals. So stop the video and see if you can think about what might happen when I bond 2 sp hybridized orbitals. First, I'm going to hybridize it. Then I'm going to go ahead and add those remaining p electrons. I'm going to add a second atom. This one is also going to be sp hybridized. Now let's see what happens when I bond these 2 sp hybridized atoms. So you can see there's my green sigma bond along the internuclear axis, but I also have a pi bond that's formed. You'll notice that this bond did not form. The reason this didn't form is because these are not lined up correctly. We don't need to get into that too much in organic chemistry, but just know that they have to line up correctly in order to make that bond. So now I get 1 sigma bond and 2 pi bonds.